basically, it makes sense to call this a two-dimensional receiver because each filter output gives me one of the coefficients in each dimension. So my noise-free filter outputs are now two-dimensional. So SI, remember this is the vector, and these are the noise-free filter outputs. These are now just the coordinates. The noise-free filter outputs are just the coordinates of the signal in the signal space. So this would be alpha I, beta I. So at this point, let's remember that these outputs, noise is added over here. And each of these outputs is connected to that noise, so each of these outputs will be noisy. So, looked at separately, so if I just had this one filter, I would have a Gaussian random variable on this line with mean alpha I and variance sigma squared. And on that line, I would have a Gaussian random variable with mean beta I and some variance sigma squared. It's worth noting that, remember sigma squared is n0 over 2ts times the norm of the filter coefficients squared. Or if I express the filter as a vector, it's norm squared of that vector. Now, Sx and Sy both have the same norm, which is 1. So the variance on both those lines is the same. It's n0 over 2ts. In other words, up here, I have Gaussian random variable with mean alpha I, variance n0 over 2ts. And on the lower line, I have a Gaussian random variable with mean beta I and variance n0 over 2ts. Okay, so this takes care of everything up to the decision device. So we have a two-dimensional region. We have a two-dimensional signal space. The decision device takes both of the dimensions as inputs. So let's say we have a signal space that looks like this. Remember last time we used what we called the nearest neighbor principle. So in other words, if I had three signals, like so, Si minus 1, Si plus 1, what I do is, if my received signal lands on this number line anywhere, I'm going to decide that it came from the noise-free filter output that's closest to it. In other words, if I drop here, if that's where my received signal is at, I'm going to decide in favor of Si. If my signal drops here, I'm going to decide in favor of Si plus 1. So what I did was I put a threshold halfway between all of the noise-free filter outputs. I didn't explain exactly why that was optimal, but intuitively it's optimal. It's because you expect lower noise rather than higher noise. So you map into the closest points. So in 2 dimensions, that same principle holds. So for instance, the difference is that now we have, instead of just one filter output, we have 2 filter outputs, so we have to express it on a 2-dimensional plane like this. And instead of threshold points like this, what we have are threshold boundaries. In other words, borders that separate 2-dimensional regions from each other. So for instance, to decide between S0 and S2, the line that separates all the points closer to S2 from S0 is just this line. So if I draw a little connector between those two, the border between the points that are closer to S0 and the points that are closer to S2 is, I go halfway down this line right here, and I draw a line perpendicular to it. Like so.
So is there a convention of writing like the way you wrote S0 to S4, or which is S0 to S8?
Not really. You can do that however you like. We're not gonna, now it's kind of meaningless to do this, writing it in order like this. So you can do this in any order you like. Okay, S1, between S0 and S1, let me draw those in with a line, like so. And the set of points that's closer to S0, the division line between the set of points closer to S0 and the set of points closer to S1 is this. S0 and S3, set of points closer to S0 as opposed to S3, the dividing line between them is perpendicular like this. So the set of points in this entire space that's closer to S0 than any other point is the union of these three spaces. So the union of this space, everything to the right of this line is closer to S0 than S2, everything above this line is closer to S0 than S1, and everything sort of to the right of that diagonal line is closer to S0 than S3. So this is the space, and it's set off from the other regions by this border. So I mentioned this term a couple of classes ago. The set of all points closest, set of all points in space closest. So if I have a set of points, let's call it script S, and some point, the set of all points closest to some S in script S, the set of all points in space, not necessarily an S, closest to S in S, closer, excuse me, to S in S than any other point in script S is called, does anybody remember the term? It's called the Voronoi region. And in this case, what I'm going to do is I'm going to say my set of points is in fact the set of noise-free filter outputs, these two-dimensional coordinates. So SI, S0, S1, and so on, up to Sm minus 1, the noise-free filter output coordinates are a set of points. And I'm going to let V sub I be the Voronoi region for SI. So in this case, the Voronoi region for S0 is the upper right-hand quadrant, like so. What do you think it would be for S1?